Hey guys, welcome to Taking Action Chapter 1. Thank you so much for joining me for my very first digital PD. This course introduces us to the 8 effective mathematics teaching practices. So let's go ahead and get started. This digital PD series is based on the book Taking Action, which explores 8 effective mathematics teaching practices. The 8 effective practices are based on 25 years of research and are backed by NCTM. These practices challenge students to become thinkers and doers of mathematics. They support teachers in building students' conceptual understanding along with their procedural fluency. And research has shown that these practices improve student learning of mathematics. So let's check out these 8 practices. The first effective practice is to establish mathematics goals to focus learning. Implement tasks that promote reasoning and problem solving. Build procedural fluency from conceptual understanding. Use and connect mathematical representations. Facilitate meaningful mathematical discourse. Pose purposeful questions. Support productive struggle in learning mathematics. And elicit and use evidence of student thinking. Our purpose in this course is just to become familiar with these practices. Each of these 8 effective practices will be explored later in depth in their corresponding course. So let's take a look at our first practice. The first effective practice is to establish mathematics goals to focus learning. Mathematics goals indicate what students are to learn and understand as a result of our instruction. Goals should identify what students are to know and be able to do. Goals should be understandable for both teachers and students. And we also have to consider how our learning goals relate to and build students' understanding toward the rigor of our standards. Everything we do throughout instruction should be gauged against the goals. And we also use goals to monitor our students' progress. But the type of goal also determines the type and the depth of the learning that our students experience. Let's take a look at a couple of goals. The 2 goals we're going to look at align to the 7th grade geometry standard G24. This standard says that students are to know the formulas for the area and circumference of a circle and use them to solve problems. Students are to give an informal derivation of the relationship between the circumference and the area of a circle. Now let's take a look at goal number 1. It has 2 parts. The first part of the goal says students will use a hands-on approach to derive the relationship between the circumference and area of a circle. The second part says students will apply area of a circle to solve problems. Now let's take a look at goal 2. Goal 2 says students will be able to find the area of a circle. Both of these goals fall under this standard. However, the learning that takes place under Goal 1 could be very different than the learning that takes place under Goal 2. Goal 1 is specific about what students are to know and be able to do. It addresses the conceptual aspect of the learning by requiring students to get hands-on in constructing and deriving the relationship between circumference and area. And it also supports the procedural because it's asking students to apply that area formula. Students experience a deeper learning under the first goal compared to the second goal, and the first goal addresses the rigor of the standard. On the other hand, the second goal focuses on the procedural aspect only, and it's not clear under that second goal if students will have any conceptual understanding of area of a circle. Both conceptual understanding and procedural fluency are important in mathematics learning, and our learning goals should support both aspects of that learning. The practice of implementing tasks that promote reasoning and problem solving supports our students' conceptual development. These are high-level tasks that require students to think and make sense of a situation in order to solve the problem. These types of tasks should be open-ended and allows our students to use their own mathematical understandings and their own strategies to figure it out. And learning is greatest in classrooms where the tasks consistently encourage that high-level thinking. We also have to keep in mind our students' prior knowledge and their current abilities when selecting these tasks. The task we select must be doable for our students, but still challenge them to reason and to think. So let's compare a couple of tasks. Task A says, our 6th grade class is selling wrapping paper to fund our class party. Each roll of wrapping paper sells for $2.50 and is packaged 12 rolls to a box. Our class sold a total of 15 boxes of wrapping paper. How much money is collected for 15 boxes? Write an equation to show the amount of money collected and the boxes of wrapping paper sold. Now let's look at task B. It says solve the equation, and it gives students 3 equations to solve. First of all, let me say that both of these tasks have their place in mathematics learning. However, when we consider which task has the potential for the greatest learning, I think we can agree that's task A. Task A is a high-level task. Students are not told to use a particular procedure. So students could approach this question using different methods: guess and check, make a table, graph, and then use those strategies to help write the equation. Task A requires effort on the part of our students. In contrast, Task B is a low-level task. Now let me explain why. It implies students are to use a memorized procedure to solve. It's procedural practice only. It does not ask students to explain or justify their answers. The mathematics students learn by doing high-level tasks like Task A is very different from the learning that takes place with low-level tasks. Next, we're going to check out the effective practice of building procedural fluency from conceptual understanding. Conceptual understanding is knowing why the math works. Procedural fluency is knowing how the math works. Fluency means students are able to flexibly choose the appropriate methods to solve problems. They understand and can explain their approaches and why they chose them. And they are able to produce accurate answers efficiently. When the procedures are connected with the underlying concepts, students have a stronger retention of the procedures, and they can apply them in new situations. So how do we build that procedural fluency from the conceptual? We build procedural fluency from conceptual understanding using a sequence of task and learning experiences. We first develop conceptual understanding by building on students' informal knowledge. We provide experiences where students engage only conceptually on the basis of what they already know. Then we give them opportunities to develop informal strategies to solve problems. This is where they can use their own mathematical understandings and their own strategies. The next activities would help students refine those informal strategies to develop fluency with the standard methods and procedures. It's also important to give students opportunities to compare and contrast different methods to solve the same problem. That builds fluency, but it also helps them to see the different connections. And students need opportunities to analyze worked examples to build their conceptual understanding, those error analysis type problems. We'll explore these strategies further in the Chapter 4 course, but I just wanted to give you a little sneak peek today. The next effective practice is using and connecting mathematical representations. Students who are able to represent, discuss, and make connections between these different mathematical representations show a deeper understanding of the math and a stronger ability to solve problems. This figure here shows the important relationships between pictorial, written symbols, oral descriptions, real-world situations, and manipulative models. Understanding these connections give our students a broader and deeper understanding of the math. Students who have that understanding of those connections are able to make sense of different mathematical contexts. They're also able to recognize the connections among related mathematical ideas, even new ideas that might not have been formally introduced. And they can communicate mathematically using these various representations, and they also understand how to interpret them. And this lays a solid foundation for modeling. Posing purposeful questions works to support meaningful mathematical discourse and elicit student thinking. Purposeful questions reveal our students' current understanding of the math. Our questions probe student thinking and encourages them to explain, elaborate, and clarify their thoughts. Our questions help make the mathematics more visible to the whole class for all students to think about and to talk about. And we can use questions to help students see the connections among the various representations. Our questions prompt students to reflect upon their own understanding and justify their reasoning. And purposeful questions facilitates meaningful mathematical discourse. So what kind of questions should we ask? How did you get that? How do you know that? Can you explain your idea? Why? Can you convince us? Did anyone get something else? Can someone tell me or share with me another way? Do you think that means the same thing? Is there another opinion about this? Why did you say that? Purposeful questions and meaningful mathematical discourse go hand in hand. So let's talk about facilitating meaningful mathematical discourse. When students are able to formulate their thoughts and share that with others, they're deepening their own understanding. Meaningful mathematical discourse provides students opportunities to share their ideas and clarify what they understand about the math. Students are able to develop arguments to defend their solutions and either agree or disagree with their peers and explain why. Students are able to hear the different perspectives from other students. They can hear different approaches that maybe they didn't think of, and that might cause a light bulb to go off. And through mathematical discourse, we can link students' prior knowledge to the new learning. Mathematical discourse engages students in the learning process, and ultimately it advances the learning of the entire class, building our students' confidence. As teachers, we have a few tools to help us generate math talk. One tactic is revoicing what students have said. For example, so you're saying blank. Do I have that right? Asking students to repeat or restate what another student has just said is another tactic. We can have students explain their reasoning or if they agree or disagree and tell why. We can invite students to add on to the conversation. Waiting, giving students the time to respond and making sure they understand that it's okay to take that time to think it through is important. And turn-in talks or think pair shares. This gives students opportunities to talk one-on-one with other students. That way every student has a chance to talk about the math even if they were not able to join in that class discussion. Giving students these opportunities solidifies what they understand about the math. But it does require teachers to be proactive in facilitating and anticipating what direction that discourse will take. And it also requires solid classroom management. Now let's talk about productive struggle. Productive struggle is necessary in developing students' conceptual understanding. Using tasks that promote reasoning and problem solving supports productive struggle. In productive struggle, students must be required to work to make sense of a situation and then determine a course of action to take when the solution strategy is not obvious. And again, the task we select should be doable for students, yet be enough of a challenge so there's something new they have to figure out. So let's talk about what productive struggle looks like. The ultimate goal of productive struggle is to lead students to understanding the math. The learning goals should be doable, but still challenge students to think and persevere through the task. Productive struggle should yield viable learning results for students. And even though the task is challenging, students should feel empowered and supported in their own learning. And productive struggle should create a sense of hope. Hey, this is hard, but it's doable, and if I put my mind to it, I can figure it out. In order for productive struggle to succeed, we must build a culture in our classroom where students understand that they will struggle and that's okay. They will learn a lot through this experience and develop perseverance to do hard things. But they also must feel supported by us in that struggle. And we have to be careful not to take over the thinking for them or tell them how to do it. They're still in charge of figuring that out. And the last effective practice is eliciting and using evidence of student thinking. This effective practice allows us to gain insight into what our students are thinking. And it's critical for us to have that picture of what students actually know and understand, because that allows us to make instructional decisions in real time to respond to our students' understandings. And we can use that insight when we develop future lessons. The 8 effective mathematics teaching practices work together to support our students' learning. This course was just an introduction to each of these practices. We'll explore each of them further in their corresponding course. Thank you so much for taking the time to watch this video presentation. Please be sure to complete your assignments in a timely manner. Start by reading Chapter 1, Setting the Stage. You have 3 assignments to complete. Assignment 1 is a Teaching Practices questionnaire. Assignment 2 has 2 parts. The first part is a required reading. You'll want to print those files out in order to complete the second part of Assignment 2, which is a questionnaire. Assignment 3 also has 2 parts. Assignment 3 is the discussion forum. So post your discussion to the forum and then complete the Assignment 3 forum verification. Thank you so much for taking the Chapter 1 Digital PD. If you should have any questions or issues, please just shoot me an email. I hope you join me for another Digital PD.